Euclid's Elements, Book 1, Proposition 13. When a line is set up on another line, it either makes two right angles or two angles equal to two right angles. So in this proposition, Euclid is considering two situations. When you have a line and you have another line set up on that line, it will set up in one of two ways. It will either set up where these angles are instantly equal to each other, in which case we know from definition 10 that they are right angles. So you have a right angle here and you have a right angle here. So obviously here you have, this is equal to two right angles. Or if these lines are not immediately equal to each other, when added together, this angle 1 plus this angle 2, here's angle 1, here's angle 2, we're saying that these taken together will equal two right angles. So they either equal two right angles directly or they equal a sum that we can show is equal to two right angles. So let's look at that case because that's going to be the far more likely case. So we have a line and another line set up on that line, and we want to show that this angle plus this angle taken together are equal to two right angles. So let's say we have CD set up on line AB, and let's say that they're not equal immediately. Well, we still can show that they equal two right angles. So what we're going to do is at point C, we're going to construct a line perpendicular to our given line AB. And we can do this because of proposition 10 that allows us at any given point to create a line perpendicular to a given line. So we're going to make CE perpendicular to AB. Well, that immediately is going to, we know that if this is a perpendicular, we have a right angle here and a right angle here. And I'm going to label this first right angle 1 and the second right angle 2. Now I want to label some other angles here. I want to label this angle here, angle 3, and this angle here, angle 4, and this angle here, angle 5. So now let's consider these groups of angles. First, let's look at angle 2. We can see that angle 2, the right angle, is equal to angle 4 plus angle 5. That is, these two angles taken together take up the same angle as angle 2. So we can say angle 2 is equal to angle 4 plus angle 5. And that gets us to here. Well, at that point, let's add angle 1, the remaining angle, to both sides. Because if these are equal, we can add equals to equals and it preserves the equality. So let's put a box around that. We're going to come back to that later. Now let's look at another angle. Let's look at angle 3. Angle 3, let's do it in black. Angle 3 is clearly equal to angle 1 plus angle 5, right? Angle 3 sweeps out this much. That's equal to angle 1 plus angle 5. So we say angle 3 is equal to angle 1 plus angle 5. And again, to that, let's add the remainder. Let's add angle 4, the remainder, to both sides. Let's put a box around that. Now what we want to look at here is we have two things equal to three things here and two things equal to three things here. When we look at these three things, we're going to see this is angle 4, 5, and 1. This is the same as angles 4, 5, and 1. So these things are the same, which means these two things, which are equal to the same thing, are therefore equal to each other. Common notion 1. Therefore, angle 1 plus angle 2 is equal to angle 4 plus angle 3. But angle 1 and 2 are equal to two right angles. Therefore, the remaining angles, angles 3 and 4, are likewise equal to two right angles. And that's what we're trying to show. That this angle plus this angle are equal to two right angles. Even if they're not immediately equal, we know they add up to two right angles. And that is what we're trying to demonstrate. So QED.